So today I want to talk about the last feature of 1D prediction, natively unstructured or disordered proteins or disordered regions. And this idea of them being important really goes back to Keith Dunker, who did a bachelor in chemistry, a master in physics, a PhD in biophysics, and a postdoc in computational biology. So you see the evolution here to the field of computational biology. I believe this is a classical example for a path. Many publications, very impressive H-index, but the real contribution from Keith is to shaping this entire field of disorder. And again, this field has different names, intrinsically unstructured proteins. There's a variety of words out there. And since the phenomenon is not well defined, the words will continue to also not be well defined, because there are so many things we are looking at. What we do know is what it's the opposite of. And the opposite is of order. Structure determines function. So in the central dogma, the information is in the genes, the gene information is put into the protein sequence is put, the same sequence leads to the same three-dimensional structure, sequence determines structure, structure determines function. That's the cycle. And in this structure determines function, what you need is order. You need always the same kind of order. And one typical image that you have for this order is the key and hold principle. So you have one protein, when two proteins bind, then they have sort of complementing motifs or complementing regions that fit into each other, just like key and hold. This image is slightly sort of diluted, if you want, by dynamics. So you know that proteins move, and this movement is on different time scales. I'll get there in the next slide. But the way to unify these two images typically is that the motion helps you to sample the conformations for the key. That's somehow the image. Again, there are different time scales of the motion. These are all the time scales of functional motion, and you see they completely overlap with the time scale of folding. So it takes a protein on the same order of time as it takes it to bind. That's an important reality of motion. This side chain rotation is another aspect of motion that clearly also relates to function. This is sampling conformation. This is sampling conformation to adopt structure, but it's also sampling conformation for further functional interactions. Now, the idea of natively unstructured or disordered is the following. Assume I have a stretch of a protein, a peptide, or an entire protein, that is such that if I now throw at two different time points, I could observe it with light, and I observed it at two different time points, what I would see are two different things. Okay? Upon binding, I adopt a unique three-dimensional structure that is regular, in the sense that now, if I looked at two different time points, I would see the same. So this sort of floppy thing that loops around there adopts, in this particular case, upon binding an alpha helix, right? This is one mechanism. Another mechanism, often referred to as fly casting, essentially, you have a loop that dangles, in this particular case, is the C-terminus, the end of the protein, that dangles around. And the loop, being unstructured or disordered, in fact binds to another protein because it reaches out very far. And we begin to see different themes of disorder. An efficient binder, by being big, by wrapping around something, could be regulated through post-translational modification. So essentially this loop that you had before here in the fly casting mechanism, you could imagine that you bind it with a sugar on and off. And then you have a switch to activate this fly casting mechanism. You can increase complexity by plasticity, meaning essentially you have two different ways of binding, and that means that you, instead of binding only one molecule, you can bind two, and that increases the complexity. And you could sort of have a model in which you have different states. So you have a more disordered, a less disordered, and one is active and one is not active, right? And by that you could sort of regulate in an additional way, simply by this adopting structure, it is no longer functional. So this is one mechanism by which you can simply steer the way you have processes started. Then there's the idea that there could be a coupled binding and folding so that the protein actually doesn't fold on its own. It folds only upon binding, and the binding helps it to fold, which again, because of the reasons that I showed before, can have functional reasons. We can imagine that there is a scaffold here, and the scaffold is used to provide the order, and on top of the order there's some event here, some additional phosphorylation event or something that triggers an additional event, and that then leads to a new binding, then this one. So you can sort of choose the pathway you get into by activating or deactivating a flexible element here. In fact, when we look at all the types of disorder, there are many more. So the ones that I showed you so far, in all of these cases, what is common to them is you have something that is stretched and it allows you to do additional things, right? But what you possibly can also do as additional things is to not do anything. So the image here is the one of an Amazon packaging. So you have some filling material. You have filling material that prevents anything from bumping into. You buy a sphere, a glass sphere, and you put some wrapping material around it, and there will be no direct impact on that. And this, on the protein level, you could do that by simply having a large thing that samples space all the time, and that acts like a buffer material. It doesn't bind to anything, and by not binding to anything, it's a buffer material. And that does happen too. So if you want, the function there of disorder is not to have a function, in some sense, not to interact with anything, which again is for buffer material a very important function. Then there's this aspect that the same thing that when you have a long loop, you actually sample a large space. And sampling large space, what could that be good for? What could that help you do?
Getting things that are in the space in a low concentration?
Yes, you can reach out to essentially increase the amount of space you sample. You have a higher probability to find things. You can find them to bind. This is somehow the fly casting if you want. And you can simply, another aspect of the same idea is you can sense a large space. So low concentration or high concentration, by simply sampling a large space, you also will see whether inside of a larger space there's an intruder, there's another protein to bind, which could be your binding partner or could be something that you avoid to bind. And again, this happens. And disorder is about all of these. When we look at the data, where the data comes from, one famous database is DisProt, where people collect proteins that have been annotated as disordered. Now, I will go back into this. I want to now go into my talk by arguing, well, assume that we have some idea that there are disordered proteins out there. There's a database where we have some. But we actually don't quite understand the phenomenon because we don't have a direct way of measuring it. For a structure, I have X-ray crystallography. Here, I will actually come to that point, whether that can be used or not. But assume for the time being, I don't have a clear data set. I don't have a clear experimental setup that gives me disorder. If so what could I think about that looks like disorder? One extreme way is loopy, what I call loopy disorder, and that goes back to work from Jinfeng Liu, who's now at Genentech, and that started with doing sequence analysis. We saw that there were long stretches in sequences that had no regular secondary structure. So one definition that Jinfeng came up with is, let's just look at things that have over 70 consecutive residues, less than 5% helix or strand. So essentially it's only loop predicted for 70 residues, again, or 65 of 70 residues, right? Ballpark. Now, when we looked at that at the time, when it was published here 15 years ago, when we looked at the PDB, there was not a single case, not a single protein that fit that criterion here. So we had to lower this. We looked at things that had less than 5% helix or strand at about 50 residues. And for that, we found four major themes. The one is you have essentially a long loop that connects two domains. Okay? Something that has no regular secondary structure and essentially connects two domains. Then there was this case of floppy ends. So you have a protein that is nicely regular, and then there's a long end standing out. This is like the fly casting mechanism that I showed you before. And then there was this wrapping loop kind of thing. So you have a regular domain, and around it wraps a loop. This loop does not look floppy because it's bound wrapping around this domain, right? But it still is, when you sort of line it up, it's a long loop, and this is another class. And the fourth class that we saw were proteins like this, where in this particular case here, it looked as if you condensed it, you would get sort of regular secondary structure, so these beta strands here would actually pair. Without it, the way they were in the PDB, they didn't pair. So there was an entire thing that somehow looked floppy. This particular case here is the most extreme example that turned later out to be wrong. So there was a mistake in the experiment. But there were things like that. And then we simply asked, now this is what we sort of assume in terms of structure, that's the way we imagine them. What if we looked in genomes for things for which for 70 residues we don't predict regular secondary structure? Do you believe we find any? Well, we find some, right? Otherwise I wouldn't have a story. But do we find many?
I think there should be quite a lot actually, because it's really, I mean, the structures that we have are basically just of the order. First, it's because we can crystallize them, etc.
And that's a very good point, and we go back into that toward the end of the talk today. That's the dark proteome story that we get into. But ultimately here for eukaryotes, a high fraction is very long loops. This is percentage of proteins, this is percentage of residues. The scales are slightly different here. So here I simply ask how many proteins do at least have one long region of this disorder of 70 and more. And here I ask how many of these residues in fact are in these 70 or more residues, and that number is much smaller than this one. The overall average is still such that at least 10% of the biomass is this strange long loop type. When I look at the cumulative distribution, I see that 20% of all the ones longer than 70 here are longer than 170. So I have 170 residues without any regular secondary structure, right? And then I, in fact, saw that many of these here are evolutionarily conserved. So that sort of suggested that what we have here is not junk. It's not something that's just going to be cleaved. It's something that has some sort of functional idea about it. Now, the next question that you then will ask is, can we predict it? Can that thing that we have, can we predict that? And one of the prediction methods was this one here. Mean hydrophobicity, mean net charge. The purple one, the pink ones are disordered, the blue ones are structured, and you all see the very clear line, and boom, voila, you have a method to essentially predict disordered regions. Okay? Any comment?
The overlap below the line on the lower, where the yellow point is.
So you want to move the line a little bit. That's not the kind of comment I meant.
No. Actually, like might this be like a twilight zone?
Yeah. There might be some twilight zone. Okay, let's go back to this. This is mean hydrophobicity. I already told you that there are hundreds of hydrophobicity indices, and I bet you between those you're not going to get the same. This is mean charge. Or net charge. No, it's mean net charge. So again, there are different ways of measuring charge. What was your comment?
No, I was just gonna say, how do you really know that it's really disordered if you have hardly any
yeah, that's a problem. And
proteins that are disordered?
I'm sorry, I made a mistake in the way I structured the talk. This is completely illogical given my structure. Yes, so let's just assume that for some proteins we have some evidence, experimental evidence, that they are unstructured. And typically those are proteins that that evaded crystallization, or there's a variety. You have CD measurements, you don't see that there's no regular secondary structure. There's a variety of ways of getting evidence. So there will be some issue. But the real problem here is something else. The problem that I'm pointing out to you. So this was not a fake data set, it was a real data set. But my point is, whenever you in your work encounter anything of that simplicity, that nobody, so when that first published, nobody had ever seen that, nobody had ever published that. When you encounter something like that, so yes, there are pearls to be discovered by you. So you also have to have the courage to discover new things, and they may be really simple. But this is too good a fit for being reality and being biology. In biology, you never have something as simple as two axes, and you distinguish so clearly between two different sets of proteins. So this was just, in this particular case, was a very, very lucky choice of data. No future data ever did fit this plot. And it was, in this particular case, clearly this was not, nobody cheated. This was absolutely, it was absolutely sober. It was absolutely clean, well done. It's just, be more careful. If things fit too good, check twice or check 3 times. The authors at that point could not have done much to avoid this. But clearly, this is too good a fit to be true in biology. But let's just develop a few methods that may go in the direction of what we believe is disorder before we know the data set of really what is disorder. It cannot be that simple, that much is clear. So one way in which we could possibly predict disorder is by predicting local residue flexibility. You know how that is called in the PDB? There's a measurement for that. Ever heard? They're so-called B values. B values measure local flexibility, and Predrag, again, hopefully is going to give a talk next Tuesday on the code protein of tobacco mosaic or virus. You see that there's a region that is blue, very rigid, and then there are 2 side regions here that are more flexible. In the NMR structures, you have seen it from different models, so each line here is one model where all the lines come together in 3D. There's very little movement. Where there are different time points, there's a lot of movement. Here you see really the movement of 2 parts of, it's not 2 domains, but it's 2 parts of the molecule moving in that direction, and this is functional. When you plot a normalized B value, then in that direction you have increasing flexibility and that increasing rigidity. There are different resolutions here. The largest set is less than 2.5 angstrom, but you see that they are pretty similar. And now the question, if we want to predict B values from sequence, we can actually not predict this value. It's too complex. We need to somehow get a reduced state model. So let's begin with a binary model. In a binary model, I predict either rigid or flexible. Where do I make the cutoff? Where do I put the line in between the two? No suggestion? What if I were to put the line in the peak of the distribution? Would that be a good choice? Can anybody argue why that is not a good idea?
Because we lose, because basically this is kind of like an extended, well, not really a Gaussian, but let's just fit it to a Gaussian. And if we put it at the peak of the distribution, we lose everything that is like right off the peak.
No, wait. So Gaussian, I'm totally fine calling this a Gaussian. But then on right of the peak is, I would call that flexible. Left of the peak, I would call that rigid. So in fact, I even created 2 classes, if it were a Gaussian, that are equal.
But it's not really 2 classes, is it? I mean, there's the majority of the amino acid of the residues is there, and they're so close together. So basically, if you just put the line, then you just make it sort of.
So you dislike the
upwards.
fact that it is so. You want to stretch it a little bit?
No, I just mean
Put
that
a factor
the
of
ones
2.
that you- All right, then you have so many that are really, really close neighbors and are hardly different. I don't know really how to describe it.
Did you understand what she said? I mean, she said it, but did you understand it?
Yeah.
And you were the only one who sort of moved ahead. So let me use different words. Let's call it a Gaussian. So there's an experimental error, right? Say the error is epsilon. If you take that as a choice, and you make an experimental epsilon error, right? Then you pick the point as the threshold at which an epsilon error, whatever size of the epsilon, is going to have the strongest impact. By choosing the maximum of a distribution, the accidental error that will then lead on this side to a flexible and rigid by mistake, because you measured an epsilon incorrect. And here the number of misclassifications by an epsilon error mistake will be maximal. If you're in the peak of the distribution, any movement of epsilon, whatever distance you have, left or right, is going to have the maximal impact at the peak. At every other point of the distribution, the same epsilon will hit fewer points. So the amount of mistakes that you make by an epsilon in classifying into 2 states, rigid or flexible, is maximally here. Any other point is better. Okay? So if you choose a point, absolutely not this one. That's the first thing that you should always remember. This is the worst one because of that. Yeah? Ron?
It's a light problem depending on like if you go to the left side, which is pretty fast growing, I don't know. Depending on how you choose.
It's a very high slope, yeah. So one thing is
might lose as well,
I believe
or-
where you're going on is if you choose the threshold too much here, there's very little left. If you choose the threshold here, there's very little left on that side. So, yeah.
I just want to say, I think it would make sense to just really look at the outliers. I mean, these are proteins with known resolution, so they apparently have a structure and everything. But mostly, I mean, you can just lie the chain through it, so you can't see them, so the disorder isn't that great.
Oh, wait a minute, we don't talk about disorder here. Now we're talking flexibility in a regularly ordered structure. So,
What is the graph?
the graph is for all the residues in 1,513 sequence unique proteins, every single residue.
Yeah, but there's resolution smaller there for these different lines, so I
Yes.
assume
So the
that-
data set is
yeah,
smaller.
The data set is, so I just assume that the data set is for crystal
structure.
Exactly, and what I'm gonna say is that for the majority is they around 0, but for the majority of these residues in there, you can just line and structure through there. It may not be perfect, but you can kind of see where it is. So if you go to the, if you chop off the tail, then what you get is the outliers that are especially wiggly. No, not that, the other one, the other part of the tail. I mean, that's with increasing, with increasing flexibility. So that would be the ones that probably also harder to see, and so are more outliers.
Oh, wait. I'm sorry, I made a mistake. So I begin talking about disorder.
Yeah.
And then said, well, can we find methods that predict something that may be related to disorder, although not using experimental data about disorder? And the first attempt is, can I predict flexible residues? If I could, maybe disorder proteins would be those for which I have 50 residues that are highly flexible, that I've predicted to be on this tail end side of things. Right? This is one way of applying that method. But ultimately, I want this method also for other purposes. Anyway, knowing which residue is more rigid and which is not is an important thing for structure. So I actually do not only want to predict the tail. I also want to predict what is rigid.
Yeah, but I meant to say that then it makes sense to make the cut at some part of the tape for these two classes, because then you have like normal residues and particular flexible.
Okay, so now we get into the next idea. So the next idea in a more generic way is, don't answer the question, just try 5 different thresholds and see where you fare best. You have to be careful in executing that idea. In fact, this is ultimately somehow what we did, because the absolute value that you get out in a two-state accuracy prediction is not relevant. What you have to put there is improvement of random, because the way the populations, so shifting this one here will shift the populations, and therefore the random Q2 will also be different. Okay, you have to remember that. But then if you remember that, you can actually see that by moving this too much here, you have a problem, because you actually can't learn, you don't have enough data. You have some, it's not that you have nothing, but the complexity of the problem is so high that this is not enough. So we found out we need to move it a little bit. In fact, what we did move it to is we sort of had 2 different modes. One we called strict and one sort of a non-strict mode. And then in our prediction we had 2 different aspects. What Predrag showed is that this is the Q2 agreement between 2 proteins in different experiments measured twice, and the B values rigid, flexible in a 2-state model agrees by about 80%. When we look at 2 proteins that have between 90 and 100% sequence identity, their B values agree to less. Okay? If you look at 2 proteins that have 70 to 90%, even less. So our prediction method will be less than that. That much is clear. What is it that we have to do as a first step? So one thing is we collect the data, we plot the data, that defines a threshold for a binary system. But now the next question is, before I actually apply a machine learning device, what would you next look at to see whether there is hope for a prediction method? This part here is something that you have to look at to sort of establish that there's, when structures are similar, 2 proteins of 90% sequence identity you believe have similar structures, have similar function. So you actually, B values, if they would be different between the 2, would not really make sense. So that's another thing you have to check. But what's the next thing that you should check in order to see, well, there's some point in doing developing a prediction method. What is the minimal, the 0 level model that you have to do? The simplest thing you should look at is in a 2 or 3 state system. So here we have actually 3 cutoffs. For this, we have one here, and everything in between. And you see that everything in between green, that's a deviation, a difference from background. You see that the greens are essentially at 0. But both the rigid and the more flexible ones, there is clearly a difference between different amino acids. So just looking at an amino acid already gives you a method that somehow can predict it. So if you see something like that, you know that if you do some machine learning device, you will have to at least improve over this trivial. This is not random anymore, but it's the lowest level prediction method that you can, by just knowing the amino acid and always predicting DE to be rigid, for instance. That's one way of reading these observations here. Or in some probability, according to the difference between red and blue. That's what you have to beat in your prediction method. When you do your prediction method, again, you do the same thing as before. You use profiles, and then you have 2 output units, rigid and flexible. You establish accuracy and coverage. You look at the reliability index, so you see whether the difference between these 2 units helps you to increase accuracy. And I have an issue here. Why? There's something. So this, I currently have an issue to read this. So the accuracy should improve over there. I just have an issue with the negative values. So accuracy increases the higher the difference is between these 2 units. That's true for the positives, that's true for the rigid, and that's true for the flexible ones. And coverage at the same time decreases. It's also expected. When we look at a particular protein here, RNase H, You get a distribution like this. The observed is green, the predicted is rose, pink, and then there's some other parameter underneath here. Maybe this is way too much detail. What I want to say, at the end of the day, we can predict either residues that have to be rigid, flexible, and residues that have to be rigid, that are important for the binding site. So in both of these cases, so the method correctly predicted either the flexible one or the rigid one. In both cases, the one that was relevant for binding, just by predicting the local stretch of flexibility. So both of these structures here, so we mapped our prediction on known structures, but the method predicted it from sequence alone. So it did not have this grouping information. It just looked at what is a stretch of flexible and rigid that is conserved. And then we consider those to be the binding site, and we simply map them here to the structures, and in both cases you clearly see the binding site. How do B values relate to disorder? The following curve of Predrag, I will zip over, shows that there is some correlation, but there is no direct correlation. So flexibility has something to do with disorder, but it's not quite the story, okay? So we need another method. And the other method is, going back to what I showed you before, is the method of 5% helix strand in 70 residues. The method, whatever, so you simply use the secondary structure prediction method. You ask, do you predict less than 5% alpha helix and beta strand over 70 consecutive residues? If so, you call it disorder. Now that method is very, very accurate. Whatever it finds, again, I will get back to that in a moment, is established as disordered. The problem is that many proteins that we consider to be disordered are missed. How could you change that? Well, you could try to see what if choosing the threshold and moving it to 30, say, right? So instead of larger than 70, larger than 30. It turns out that then you make many mistakes. So you cannot do that. So the threshold 70 was chosen such that the number of mistakes was essentially, at the time when we chose it, we didn't make any mistakes. So we cannot do that. What else could we do? We could do some machine learning. But how could we do this? What would we learn on? Oh, that already gives it away. How could you machine learn a method that sort of predicts this type of loopy disorder for things shorter than 70 residues? What would you put into your positives and your negatives? So your positives are things that you know have disorder, and your negatives are things that you know don't have order. Again, I'm building a method without knowing disordered proteins. I only know this.
Well, your positives, I suppose, would be your known helical or strand structures.
PDB, so negatives. I call them negatives because predicting disorders, that would be the absence of that.
Yeah.
Mm-hmm. Exactly, that is one answer, yes.
And your positives would then surely be the loop regions that you have.
Ah, that didn't work. So that didn't work. So what we did use, however, is exactly these. So the true were all the predictions of 70 and more. And the false, or the negatives, were in fact the ones in the PDB. Now, I have to put two things here that's very, very important. The first one is, we know that what we predict is not enough. We want to predict something new, right? And all we need, all we put into our data set to learn to find something new is what we have. This may not be very smart. I mean, this may be very circular, right? It may very well be true that the ones that are shorter have very different features. And they are not in our data set. Because all we put in our data set are the things where we are very sure in our prediction. That's one problem. The other problem here, that's the problem that in the ones no, wait a minute. That's the problem, that in the ones that are true, they are false in some sense, because they are clearly missing what we're after. Now there's also a problem here, because in PDB there is disorder. And I will get back to that. There's a way to identify disorder in the PDB, and we completely ignore that one too. So then the question becomes, yeah?
But I'm confused right now, especially about the last slide. Yes. So you want to predict the disordered regions,
Yes.
and you want to predict those for sequences that are larger than that are shorter than 70 residues. And what you put in there is as your negatives, the whole PDB.
Yeah.
So all sequence data all structure data of the PDB.
Yes.
But as you have already said, there is disordered regions in PDB.
Yes.
And then as your true class, so as a disordered region, you say take all predictions in entire proteomes. But what does that mean? I'm puzzled by the semantics. I don't know.
Oh, so I apply this threshold prediction here for entire proteomes. I essentially predict every single protein in every single entirely sequence organism. I use entire proteomes to avoid. I could run UniProt, but then I would have to sequence redundancy reduce. By using entire organisms, I sort of keep some redundancy and some I remove.
Oh, you mean all predictions of disordered regions in entire proteins?
I apply this idea here to every single protein in entirely sequence organisms.
Oh, all right.
I can't remember how many we had then. In those days, this was hundreds. So today you have tens of thousands for which you could do that. Okay? But again, it's very puzzling, because ultimately our entire positive set is composed of something that we already have, and we want more than that, right? We just hope that there is something in there we can learn from, okay? And that ultimately is the question here. How can a data set with many mistakes be machine learned? And the answer is only if there is a consistent signal. In fact, it could even be true that there is a systematic error. So you don't even need to avoid that the error is white noise and random. It could be that there is a consistent error. If the signal is consistent, the positive signal is consistent enough, then the machine learning will ignore the error that is not random, or could learn to. Okay? Or may not, but it could learn that. And this, I'm trying to go through a couple of slides, and this is one that I will go through. Let me just state in words what it shows. It shows that the method actually succeeds. First, it succeeds in finding this loopy disorder for 30 residues. And it can distinguish between a 30 residue loop that is normally structured and a 30 residue loop that is of the disorder type. I can do that. So it completely succeeded. Let me show you another aspect of this, an application, and that's the idea of hubs and disorder. On the macro level, you sort of want to plot more binding partners, and on the micro level, you assume that you can bind to more partners if you have more binding residues. So I look at a protein, I predict which residue in this protein will bind other proteins, and the more residues will bind other proteins, the more binding partners I expect. And I somehow expect a fit like that. Now, not quite that way, and that brings us back to the annotation from Mark Vidal in date and party hubs. Date hubs are proteins that bind many other proteins with the same binding site. So the idea of a date hub is in a date you meet different partners, have different dates, and it's always, you always look at them with your face. And then you go to the next one, and then you go, but it's always the same part of you that sort of looks at them. While in a party hub, in a party you talk to many people at the same time. So people are standing left and right of you, and you're talking to all of them at the same time. There are clouds of people talking, everyone to each other, right? And in this notation here, you would expect that the one where we have more binding sites leading to more binding partners is in fact the party hub. While the data hub is one binding site with a certain number of binding residues, and you bind with the same thing to many other hubs, and you will not see that one, right? And that is actually work that began with Janai Ofran and Avner Schlesinger, and Janai followed up experimentally for many years on this and nailed the story. So what I'm showing here is just the preliminary results that remains unpublished. Janai has now published this as an experimental setup. So, and what essentially it shows here is for date hubs, you have, so now the next question becomes, how can you be date hub? So how can you create the same residues that bind to many things? And the answer here is you can use disorder. The loopy type of disorder is in fact enriched, and I'm confused by my slides at the moment. I condensed too much. This is the wrong slide. Non-hubs, party hubs, date hubs. So this is something else. I'm showing you the wrong slide. Anyway, on the right slide, and here's the right slide. I just should have taken that slide off. On the right slide, what you see is that if you have more interacting partners, the type of loopy disorder in dark green here, that's another disorder prediction that captures another type of disorder. So this is highly overrepresented for proteins with more disorder. And the next one shows this for other prediction method. Long story short, disorder is one way to have one interacting site with many binding partners. Okay? And in particular the loopy type of disorder. Yes?
Different binding partners include or mean only different proteins which may have the same binding site, or actually different binding sites which also fit the same pocket?
So you mean, are you asking about the partner now?
Yeah. Somehow specify what the partner does or does not have the same binding site. Obviously, it's
so
universal binding site.
No. So the idea is that you have a binding site with which you can adopt to different shapes. You also adopt a little bit better to the same, but you adopt to different shapes. That's the primary idea. And now, so here's another story, and that's the story about contact maps. So if you want something to be wobbly, you can only be wobbly if you're not constrained by contacts, right? If you usually there's some cable that I can use for that. So the more contacts you form here, the more this thing can no longer move. Because it's constrained here, constrained here, constrained here, and then it cannot move. So essentially by the amount of a contact you form to another residue is a constraint. By the amount of constraints, you're constrained. Okay, it's as simple as that. So what if we could simply predict the constraints of a residue, so the contacts, and that's work going back to here, Marco Punta and Avner did that together. So Marco had developed a method that predicts from sequence contacts. That is not good enough, and we will not get to this in this lecture. These types of methods are still not good enough to really predict a 2D contact map that allows us to predict 3D structures. More recent approaches can do that. What Marco did never got anywhere near that. More recent approaches can do that for some examples of proteins. So we now have maybe something like 50 proteins or a little bit more than that for which we can predict 3D structures from sequence alone through contact predictions, through evolutionary couplings, and I will not cover that in my lecture, so this is sort of the fast way of saying that. This is an early precursor of those methods. The downside with these new methods that do evolutionary couplings is they are not applicable to many proteins. So they are still only applicable to very huge families. And for them, let me define huge. For those methods, whether you have 10,000 or 100,000 makes a difference. So 10,000 is not enough. So they 10,000 members in the family, and they want 10,000 not identical members. So this is really huge families, and for those it works. But anyway, so we are back to a time when there's a simple prediction of so there's a residue number, and there's sort of a shady contact prediction. There's one that is dense and one that is less dense. At particular proteins, we see that they differ in the overall predicted density of the map. And then we say when we have a region where the density of the contacts is low, so such as in this Miocene here, the contact propensity predicted has some propensity, and then there are regions where it's low and there are regions where it's high. And when it's low, we call that disorder. There's another method out there called IUPRED that uses, in fact, not another method. IUPRED started this idea of using contacts, and IUPRED started this in a more generic way. So IUPRED argues some residues have a higher propensity for binding other contacts. This is independent of what other contacts are in your protein. Okay, and simply uses that to again predict disorder by low propensity for forming contacts. And in fact, IUPRED is one of the best methods to predict disorder. And IUPRED again does never use essentially for fitting, has one parameter, essentially the threshold, but other than that it doesn't use any knowledge of known disordered proteins to predict disorder. It simply predicts essentially low contact propensity, and it turns out that this maps to disorder very well. And this method here does something like that, but now it's specific to that protein. So we predict for every single residue the other binding partners, and then say in that particular protein we have a threshold. Okay, and IUPRED and this method that we coined UConn here have some overlap and some differences, and this is knowing the structure. Both of these methods would, for instance, see that this transcription factor that forms a long coil here is disordered, while the method that clearly doesn't see it is not on here. But these two methods are best at seeing that, because ultimately the point coil helices can melt easily. So hydrogen bond formation between these helices is not very strong. The hydrogen bonds inside of a helix are strong. Between the helix, the contacts are not strong. And that ultimately is because the helix is stabilized by I and I plus 4, I plus 1 and I plus 5, and blah, blah, blah. So you have many hydrogen bonds, right? While between two helices, you can sometimes get away with three hydrogen bonds. When 2, 1, 2, in this particular case, 2 hydrogen bonds here. And they melt easily. Okay? So they can get apart easily, and that is why it feels like disorder, because they can come apart. Okay, so far I talked about 3 different methods that, bless you, that somehow predict disorder without having ever really used disorder or annotations about disorder. So let's talk about what experimental handles there are. The first one is the Dunker hypothesis from Keith Dunker, and that hypothesis is that residues not visible in 3D structures are disordered. So the logic here is I cannot see a particular residue because it moves. So when you do X-ray crystallography, you need you have many copies of the same protein in the crystal lattice, and you have a diffraction of X-ray crystallography of the X-ray beam, and there's a clear signal comes only when all of them have the particular residue in the same place. Then it's a coordinated scattering. However, if one molecule has this residue like this and the other one like that, then the combined scattering is confusing. So essentially what you see is nothing. Okay, you just don't have electron density, because you don't have a consistent electron density, okay? And that was the argument. Everything I don't see is disordered. And this everything I don't see is disordered when we plot disorder versus order for this, so everything I don't see versus everything I do see, you see that there's a big difference between different amino acids. So even that you could predict. Now, going further, there are other methods that you can use. You can use CDs for seeing that there is just no regular secondary structure. Actually, CD mostly sees alpha helices. Then there is NMR that you can use for the dipolar coupling measurements. So essentially, that is a lack of contacts that you see. There's some small angle X-ray scattering. There's limited proteolysis, so you simply cut and see whether things are connected. There's some fluorescence and infrared spectroscopy techniques, and all of these are low resolution. All of these help for particular proteins to gather all of these experimental data to say that protein has a region that is disordered. And essentially they collect one by one. So none of them is high throughput, and none of them actually has a protocol by which it says the output is disorder. All of these are sort of indirect means of capturing some aspects of disorder. Okay? And that all is collected in this database DisProt. When we have DisProt, a database, you can immediately apply machine learning methods. One is meta disorder, but ultimately here's a table. This is a very outdated table. These are different methods that predict disorder. There are many, 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 many more of these around. The problem is we have one data set, everybody uses the same data set, and there actually is a problem because then ultimately the kind of thing you see on a ROC curve, everybody essentially has a similar ROC curve. In this particular case here, we looked at about combining a variety of methods, the ones that I talked about, and you do a little bit better than everybody else. But is it significant? It's unclear. What remains clear is disorder is very important, and what remains also clear is from whatever we do today, there's still sort of types of disorder we don't capture. So there are many challenges left, and the field in some sense sort of turns a little bit in a circle for some part of it. Most important really, and I'm only going to sample a very biased subset of the results, are the applications. So what can we use the existing methods for? What can we learn from it? So there are different types of disorder. I talked about that before. And let me skip over those. I thought the first statement here is, or the first question, or the first assumption is that maybe disorder relates to something like an atom of complexity. Maybe disorder is a way in which organisms can become more complex, and evidence for that is on this one here. So two different methods to predict disorder in red and blue here, MD and the IUPET, whatever they are, but you see they differ very much. So now what I'm asking is, in entirely sequenced organisms, for all the entire sequence of organisms in eukaryotes, bacteria and archaea, what fraction of proteins has one region at least 30 residues long that is disordered? And so these two methods differ, but what is most important is that for both methods, the eukaryotes are very, very different from bacteria. Okay? So between 36 and 43 in eukaryotes, and between 7 and 13% in bacteria. So bacteria, prokaryotes, have much less disorder than eukaryotes. And that is one of the reasons why people argue this is one of the elements for creating complexity. And one example is what we already talked about, and in some sense is exactly the answer to your question, Ron, is the molecular recognition element, more, again from introduced by Keith Dunker, where you have a region here that sort of can glue together two different regions in different ways. And Keith has assembled a lot of data on how important this more mechanism. Yes?
I would like to make a case for the complexity of bacteria. don't know if it's...
Let's make that point in a moment. I'm not entirely sure. So the point that I want to make here is by increasing the number of interactions that you can have, you increase the local complexity. It does not mean that a eukaryote is more complex necessarily than a prokaryote. But so one argument that people have is, in fact, prokaryotes cannot do that on that level because there's just one compartment. When you have different compartments, you can regulate, sub-regulate things differently. Plus, in prokaryotes, the argument is that a lot of these disorder proteins would be recognized as junk and would just be eaten up. While in the eukaryote, you have a complex machinery of digestion. So, meaning that you introduce a system that can do more things. Now, does that lead to a definition of the system is more complex? And I believe this is something where we are where things get very muddy.
If I may, the argument that I was about to make is that bacteria might not be able to do as much as eukaryotes. However, they don't have to because they are specialized in one task maybe, but where the complexity comes in, that's with the mutational rate that is tied into their reproductive cycle. So they chose to solve the problem of having to do different things and a lot of different things in being able to quickly reprogram themselves through a different reproductive cycle and higher mutational rates.
I believe this issue of complexity is one that is sort of slightly misleading, I admit that.
I think in this sense it just means that you have to do a lot of different tasks all at once. Because when I think of the proteins here, larger animals, they are sort of separate by different tissues and different sort of what they have to do, and they have to a lot more partners, and it's all very subdivided, and so you need proteins that probably can sort of communicate in between, and bacteria don't need to have that.
So let me turn this around, and we can begin at this slide. So of this thing, disorder, we have much more in eukaryotes than in prokaryotes. Okay, and it brings up the question why. What is it that we gain from it? And ultimately, what we gain from it, we can do something more, something new. And that is what people tend to say or relate with the word the complexity increases. And maybe you call us at that point, they cannot define complexity, and maybe we should stop the discussion here. And I believe, but ultimately, the question that remains important here, why is this so high? What is it that we gain from it? And ultimately, we do not have the answer to that. So we have examples like the one from Moore. We have examples where proteins do some things that they cannot do in prokaryote. We do know that in prokaryote many of these proteins wouldn't survive, so prokaryotes couldn't have them. But still, this is an amazing jump. And despite many years of research, it is still not quite clear what exactly this jump is.